Okay. First case, make sure you can do the same thing on paper by yourself. Close it at T0. What's going to happen? You got a VC0 there. It's non-zero, R. Asking for VCT. The easiest case. You just have to know. So the three equations, after we go through all the summary today, I will put it on the in-class exercise next Friday. So they are not bonus points, but they will definitely be on the final exam because this is just all the fundamentals. Why we are doing so for the 2 weeks. It's basically everything, covers everything. So the three equations, no cheat sheet. You just have to memorize it. But eventually in the final exam, cheat sheet will be allowed. But for the in-class exercise next Friday, no cheat sheet, right? Just the three equations. I write it down on the paper. It's already given. So what's the first one? It's not counted to a grade. Remember? I told you it's not a quiz. You're not supposed to do it in the testing center. So it's not a quiz. It's just an exercise to prepare for the exam 2 and also the final exam. So what is this? It's natural response, right? Natural response. What is the equation here? You need the initial voltage times what? The attenuation factor, right? Minus T over RC. It's not changing. It's always like minus T over RC. It's always like that. And RC is called what? Time constant. Okay? What's the second case? VC0, there's a VC0, there's an initial voltage stored in the capacitor at the very beginning, T0. You got a V, what? Can I call it VC final? VC infinite? Why? If I close it and let it sit there for 100 years, what's gonna happen? What's the voltage across it? It's gonna be the source, right? There won't be any current anymore. It's already fully charged. Like you have something you want to dump you have a water tank or whatever, like a pipe or water. You are filling this bucket with water, right? It has a finite amount of storage in there or volume, so eventually it will be filled up. So eventually the voltage is not changing anymore. It will be exactly this voltage. But you can also imagine that it's just a disconnect circuit. For DC circuits, it's disconnected. In here, even though close the switch, it's still a disconnect circuit. No current, no voltage drop. So whatever voltage here will be the same voltage here. So this is called what? What is the name of this case? Step response. Or what? Forced response. Okay. What's the equation dominating the behavior here? So there is a initial voltage, okay? Doesn't matter what that is. There is an initial voltage. So VCT, we derived it on Wednesday. Okay, so today we're not doing this for capacitor because we have to do the inductor one. So VCT equals what? And then the attenuation factor here, right? If it's telling you from this case, there's a third case, which is just given that VC0 is 0, so there's no initial voltage stored in the capacitor. So then it forms a very simple RC circuit. It's still step response because it's like a step. When you turn it on, the voltage is DC voltage. This is like a step. So that's why it's called step response. Okay? And it's also forcing the voltage to be the final voltage eventually. So that's why it's also called forced response. So however, if there's no initial voltage stored in the capacitor, it's just 0 volts at the very beginning. Nothing. Then you turn on the switch. It's basically a power supply. You just turn on the switch, right? You supply power to whatever the load is over here. So that's called step response. If no initial voltage, what this becomes? This becomes to what? VCT equals what?
VC infinity times 1.
VC infinity plus VC infinity what? This, right? And this is also V infinity 1 minus. Okay? This is one special case from here. Is this a special case from here as well? Take a look at it. Think about it.
What's the question?
Hmm?
What was the question?
Is this one, the first one, the special case from this as well? Why? Is there initial voltage? Yes. It's discharging the natural response. However, you close the switch, it's trying to discharge. However, this guy is trying to force it to something else. No freedom. Has to be forced to do something, which is something you don't like to do, right? However, if the voltage source is 0, it becomes the same case.
Could your voltage source just be less than whatever your VC naught is?
It doesn't matter. Eventually, you'll be forced to this voltage. Yes, it's possible. It could be less, could be more. Doesn't matter. But eventually, because this is supported by what? The power plant. Right? So the power plant will continuously supporting. So the charges over here, if this is more than this, will be eventually discharged over time. Because it's pushing charges towards this guy. Remember, the internal resistance is 0, so eventually it's dumping charges to ground through the power source. If the voltage here is less than this one. However, if this one is larger than this one, it's going to push the other way, it's going to charge up this guy and eventually force it to be the same voltage level as this guy. So it's like a balancing over time, depending on which one's larger and smaller. But eventually, it will become this voltage because this is supported by the power plant. It's plugging into the power cord. However, this is also a special case here as well. If you look at the equation, could anyone tell me how do you want to make this one a special case here? And how and why?
VC infinity equals 0.
Yeah, so there's no forced source. Then what's going to happen? It's exactly the initial voltage times the attenuation factor. Eventually, it's still the same thing, right? So just figure out this guy, then you'll know all the cases. So that's everything about capacitors. And I talk about we just don't have time to run the simulations. This is just beautiful, I told you guys last time. Because all these digital circuits are actually driving a RC circuit over time, like the CPUs. The reason for that is you have the cables are not ideal conductors, so they have internal resistance, and all the cables has a rubber shield and all the silicon dioxide in the chip, so they are forming dielectric materials and forming capacitors, right? So basically, all these capacitors and resistors are everywhere. Because eventually, when you are driving a CPU with a high frequency, eventually it is actually driving an RC circuit like this. So you will have time delays. You have time delays. The time delays is causing problems. So this is the actual digital circuits pulses. It won't be a sharp pulse like this. There will be time delays because of the RC circuits and charging and discharging the caps. So since I don't have time to run the simulation, okay, if you look at this one, so the attenuation factor here, what that looks like, if you draw the curve here, it's a e to the minus t over c. It's a minus first, right? So that looks like this. Agree with that? Okay? So if you use 1 minus it, so here's a constant, 1. So if you use 1 minus this curve, what you are getting? Is that correct? Right? So if I run a simulation, you are going to see this. I give a step, I give a power supply, I switch it on, but eventually the response looks like this. And that is why. So your digital clocks are getting attenuations, getting time delays. This is a time delay. So you cannot run your digital signal faster or shorter than this time delay. It won't be able to charge up. So for example, you want to run it faster. I want to run it this fast, digital circuits. It won't happen because the time delay is already longer than this. That's why it's critical to know this, okay? I think this is a summary for capacitors. Now let's move to inductors, and we'll run some examples in homework 8, so you will be fine for that over the weekends, right? So for inductors, let me start with the natural response. This is easy if you have learned that capacitor stuff. It's very similar. We got a voltage. So there's a ILT is also modeled as a current flow into the inductor. R, RS, VS. At T0, you switch it here. So at 0 minus, before T0, the circuit looks like this. There will be an initial current running through the inductor. Why? It's just a coil. What is a coil? When there's an AC current, it will generate a magnetic field, and following this one, it's generating a voltage called VLT. VLT is what? Same thing, similar to the capacitor's equation. You just have to memorize it. Sorry for that. So it's L d I t dt. Okay, for VLT. L d I dt. For capacitor, what's the capacitor's equation? Remember? It's ICT equals C dVt dt, right? But for inductor, it's VLT equals L di dt. Over time, whenever you keep it for a long time, you turn it on and keep it there for 100 years, what's going to happen? There's no alternating current anymore. It's a direct current. And this is just a coil, it's copper, like a wire. So the voltage over time, the voltage across it will be what? 0 volts. It's a wire, no drop, no resistance. Over time. It's just a DC circuit with 2 resistors. What's the current? I equals VS over RS plus R. Okay? So in the homework problems, you'll see terms like the switch has been here for a long time. It's the same thing like 100 years later, right? It's a long time. So which means it's been there for a long time, it's already all set. It's not changing anymore. One thing you need to know is inductors will block, so capacitors will block what and pass what? Block what? Block DC, right? Direct current, which is a DC voltage, static voltage, will be blocked because of disconnect circuits. If you run AC voltage across it, it's pushing charges back and forth. So on one plate, and it's going to repel charges on the other plate as well. So it seems like it's passing the AC voltage physically, but actually it's not. Okay? For inductors, it's different. It's passing what and blocking what?
DC blocks AC.
Yes, so it blocks AC. Why blocks AC? So whenever it's trying to make any changes, it generates a magnetic field to against it. Okay, it's generating a magnetic field and then a voltage to against that change. So that's why it blocks AC but pass DC. So for DC voltage, if you add a voltage, just DC voltage here, it's like what? It's like a short circuit. It's shorting the two terminals of the battery. It's going to generate a lot of heat over time. So this is very useful. I'll let you know one story if we still have time. This is one board I sold to a company to use inductors to block AC noise from the ground. I'll show you if we still have time, since I don't think I'm allowed to do too many other interesting things in the class. Just so many materials to cover. But can you understand here? Capacitor blocks DC voltage and inductor blocks AC voltage. Okay? Keep that in mind. So that's why here, eventually it becomes, it's a what? It's a DC, right? It's a battery, it's a DC. So eventually it's just a what? It's passing DC, so it's a wire. All right, if you switch it here, at T0, so this is T0, it's a 0 plus, right? So switch it here, it becomes this. And what's gonna happen? What is the response? What's the name of the response here? So initially, because it's been flowing like this all the time, so initially there's a IL0 flowing inside the inductor. So it has an initial current stored in the inductor at the very beginning, because you had this source running current into it. So there's an initial current in there. Whenever you switch it over here, there's still an initial current in there. It's not changing instantaneously. So still an initial current flowing into it. It's the same branch, so the current is going to flow that way as well. So what's going to happen? It's a voltage drop, right? There's a voltage drop. So you can use what kind of equation to calculate the response here? What type of law you're going to use, which you have learned in the semester? You have learned nothing? Or you learn everything but you hate everything, so you forget it? You only remember the things you are interested in, right? Like SpaceX just launched a rocket, you're interested in that. Yeah, I'm too. I want to probably go there during the break, winter break. All right. KVL plus minus. So that will be ILT times R plus what? VLT. So what is VLT though? LDIT dt. Right? So this becomes RILT plus LD. No, let's use this. IT dt equals 0. So RL minus dt equals what? Equals 1 over ILT DIT. Is that correct? Yes. What's next? Is there initial current in here? Yes. IL what? 0 to what? ILT. Here, 0 to T. Minus RLT equals natural log ILT minus natural log IL0, which is natural log ILT over IL0. To ease exponential, you're getting ILT over IL0. Eventually, so we're getting the natural response for the inductor, which is ILT equals IL0 times e to the negative t over what? L over R. So now you know that the inductor's time constant L over R. It's called tau L over R. For capacitors, time constant is RC, right? But for inductors, it's L over R. It's another thing you need to know. L over R, because it's RL here, so that's why it's a T over LR. L over R, which is this. Very similar, right? Very similar format. If I can do it, you can do it as well. These are smart. What's the next case? Step response, right? You know, if you are sitting in this room, you are already like at least 1 out of 100. If you just grab 100 people on the street, you are already 1 out of 100. For people who are the top students in the class, probably it's 1 out of like 10,000 already. They probably do know. Only like 1 out of 100 can do engineering. Any places. US, China, anywhere. So be proud of yourself, okay? This. Step response. The only difference is we are adding a source here, right? So VS1, VS2. You switch it here at T0, R. There's initial current, but eventually it becomes ILT. So T0 minus is what? VS1. Could you tell me what's the voltage across it over time, or before zero, before time 0? So you'll see that before time 0, it's been there for a long time. So what's the voltage across it? Voltage. No voltage. Inductor is a wire. No drop. Right? Before you close. So before you switch it here, it's been there for a long time. Inductor is a coil, just a coil. If it's not changing, V equals what? If I is not changing, no voltage, right? So before I switch it here, there's no voltage, but is there a current? Like IL0, is there a current? Yes. It's a wire. A wire still deserve a current, right? A wire doesn't deserve a voltage, but deserve a current. It's just a VS1 over R, right? No voltage here, just the one resistor in the circuit. So 0 plus is what? Is there an initial current? Yes. What's the current? This. Is it changing over time? It must be changing, right? So that's the goal here. We want to find out ILT for this case. So what's the name of this case? Step response or forced response. How do we find it? KVL? It's just KVL. Just find out the voltages and list the equation and derive it. It's pretty simple, right? So what's the first voltage? Minus VS2. What's the second voltage? It's just I times R. So what's the I? It's just ILT. Whatever it is, I don't care for now. I'm deriving it. What's the voltage? It's this thing, right? Equals what? 0. So let's move things around. Divide by R first, minus VS2 over R plus ILT plus L over R. What else we can do here? what else we can do here? Move it. Move it. ILT minus B as 2 over R, right? Equals minus L over R. Next, add a minus sign of it, so you have to move it to the front as well. So the integrating limit has to be changed as well. Make sure it's right. I'm gonna move this one here, so I don't have to. Let's just keep it consistent. I'm moving this sign inside here. Okay. Then we add this one to it. I know this is the most boring part, but you don't have to derive it. Just make sure you know how this is getting derived in the future. It just this solves 100% of the problems almost. You don't have to do it, okay? Since I just have to show you how this works. So now it becomes easier because now they are all the same. So I can directly use almost there, almost there. Okay. E is exponential here, so this becomes move to the left. Right? So, done. ILT equals still the same format. not RC anymore. It's L over R. This is actually mentally easier compared to other circuit analysis methods because it's just almost every time just repeating again and again. It's the same thing, right? So VS2 is what? Is that VS2 V infinite? It is, right? So VS2 over R is what? That's the final voltage. That's a resistance. So VS2 over R, because eventually after 100 years, this becomes a wire. So VS2 over R is what? It's I infinite, right?
How does the raising the negative RL using e to the power of that, how does that make that negative 2 over 4R?
Where?
In the final equation, you have E is equal to E raised to the power of negative t over 4R. How does that happen?
Oh, it's here. I just do the E's exponential on two sides, right? On both sides. So the natural log is getting removed.
Yeah, I see the natural log, but how does E go from E to the negative RL over t to, in that equation, it's negative t over...
There's no 2. Where's 2? This is L.
Oh, okay.
Sorry. Yeah. Right. So VS2 over R is actually IL infinite. Right? So this is IL infinite actually. So eventually you're getting, remove the minus sign inside. So you can flip it. So you're getting IL infinite minus what? IL0. Still the same format. Same thing. Minus or plus? Plus? Where did I get the plus?
The negative minus.
Oh yeah. All right. Step response for inductors. Now we are 100% done. Happy? You should be good for the tutorials and homework assignments. Let me run one example for you and see how that works, okay? All right? Look at this one. I'll let you know. Instead of directly diving into the problems, now we know what all the cases are. It becomes easy. Now you are looking at the problem. Easy. What's going on? The switch has been here for a long time. Okay, I'm gonna ask you some questions, right? Switch has been here for a long time. At T0, you open it. Okay? So now, T minus zero, what's the current? So see the current is being labeled as going up. Okay? It's going up. But however, if this is closed for a long time, what's really happening? This is what? Zero what? 0 volts, but the current, is the current 0 as well? No, it's a wire, right? It's a wire. Replace it with a wire. So this guy is shorted. This guy got shorted, so this is gone. So you basically have a very simple resistor network like this. Are you able to find out current in here? Yes. Are you able to find a voltage across it? You don't even need to calculate it. 0. Okay? Make sense? So got current stored in the inductor. It's flowing that way, even though the current is labeled that way. However, you know that it's trying to trick you, right? You know it's not true. It's actually that way. You just negative sign. Just add a negative sign over it. So at T0, you open it. What's happening? This part is gone, right? You got something initially stored in there, and you got a resistor. Just a resistor is very simple. So eventually the initial stored energy or charges will be discharged across the resistor or through the resistor. So what kind of response it is? Natural response. The easiest equation without all these infinite stuff, the terms. Just what? What times what? I what? IL what? Times what? Over what? Done. So sometimes I ask you to find out the R. Where's the R? Very simple case. The first problem in the homework. That's why it's super simple. It's just 2 ohms. If you see a very complex resistor network, you should still be able to find out the Thevenin's equivalent or whatever equivalent resistance network, right? Make sense? So this is what? This is IL what? T. So this is ILT. Okay? Clear on this problem? Any question on this? No? What is IL? So what's the time constant? What's the time constant? Just L over R. What is the value? L over R. What is it? For what? For a minute what? Seconds. Okay? So this is asking the percentage of the initial energy stored in the how much? What's the percent of the initial? What's the percentage of the initial energy stored in here is dissipated across this resistor after 3 milliseconds? How to calculate that? Energy dissipated. So how to calculate energy of the inductor? E equals what? Right? A half times I squared times L, right? So this is IL, which is IL0 square times e to the negative 2t over tau. You plug this in, right? Plug this in here. These are all constants, it's not changing anything. This is attenuation factor, it's less than 1. Right? So that's the energy stored in there if you plug in 3 milliseconds in it. It's attenuating over time because there's the I0 at the very beginning because the current is attenuating. So you plug in here, the energy is attenuating this way, probably more aggressively, but similar way, right? And eventually when it reaches 3 milliseconds, you can find out how what's the current energy in there. So 1 minus it will be the energy already consumed by the resistor. Make sense? Because this is less than 1. So what you're actually doing is because there's the initial current stored in there is a half IL0 square times L. That's the initial one. That's the initial one. So minus whatever has been whatever you have now, which is a current energy. Divided by the initial energy. So you get the percentage of the energy dissipated already, the one lost, circuit lost across the resistor. Make sense? What about this one? So before T0, it's been open for a long time. If it's been open for a long time, what is I0? I not or I out. What is I0? 0 is open, right? Open circuit, no current. What's the current here? Can I calculate it? Yes, it's just a wire. It's been there for a long time, just a wire. Right? Any voltage? No, it's a wire. Okay? If you close it, what's going to happen? If you close it, at t0. Let's see, what is I0? How to calculate I0? Because electrons can travel very quickly, right? So when we close it, immediately this guy is going to contribute the current through I0. Does that make sense? Okay? What about this guy? It's also contributing. Why? Because it's going to generate ILT. So what's ILT0? So what's ILT though? What's IL0? Let's say what's IL0? So keep that in mind. The current in here after you make a change, the current in here is not going to change instantaneously. It's not changing instantaneously. It's going to stay at the same current compared to 0 minus. So for here, IL 0 minus equals IL 0 plus. It's not changing immediately. So do you know IL 0 minus? Yeah, it's just a calculation. A voltage source with a several resistors, right? This is the wire. So definitely you know this. So if you know this, you know this. It's not changing instantaneously. You got a current here, flowing to where? Here? No, it's open circuit. Flowing to here? Yes. Okay? So we'll close it. Because of this contribution, there will be a current flowing here, and there will be a current flowing here as well. Oh, let's say flowing here. So KCL. Because this is the ground, it's directly go back. It's going here. Okay? You got two current contributions for IO 0 plus, which is two currents. Keep that in mind. Any questions by far before we call it? Any questions? No? It's Friday enough for today. Remember that next Friday there will be an in-class exercise, and it will be you just have to know all these natural response and step response equations for the exercise next Friday. Okay, that will be the end at the end of the lecture. I'll give you that 5 minutes exercise.